Welcome back to the channel. What you are about to hear is the story of one of the most ambitious underground engineering projects ever attempted by human civilization. A system so vast, so complex, and so quietly invisible that most of the world has never heard of it. This is the story of the Metropolitan Area Outer Underground Discharge Channel, the machine that saves Tokyo from drowning. This is not just a tunnel beneath a city. It is a subterranean cathedral of concrete and steel, a hidden river system engineered to swallow entire floods whole, to redirect the fury of nature through chambers so large you could park a jumbo jet inside them. It is not infrastructure. It is a second city, built underground, designed to die so that Tokyo can live. Imagine a city of 14 million people. Imagine 5 rivers running through it, all of them prone to catastrophic flooding. Imagine typhoon seasons that dump months of rainfall in a single day. Imagine soil so soft, so waterlogged, and so geologically unpredictable that building anything beneath it feels like engineering on a living creature. Imagine a city that flooded dozens of times in the 20th century, streets consumed, homes lost, lives taken. Imagine all of that. And they decided to build a relief system so far underground that most citizens walking above it have no idea it exists. Before we continue, make sure to subscribe to the channel so you never miss another deep dive into the world's greatest engineering feats. Stay with us until the end, because what they discovered when they finally switched this system on for the first time will genuinely surprise you. At first, there was only earth. No tunnels, no chambers, no pumps. Just the deep, dark, waterlogged clay beneath the Saitama Prefecture north of Tokyo. No blueprints had ever been executed at this depth, at this scale, in this kind of ground. Just compressed soil, ancient sediment, and a problem that had been building for 100 years. The problem was simple to describe and almost impossible to solve. Tokyo sits on a floodplain. 5 rivers, the Kanda, the Shirako, the Kuroyadori, the Moto Arakawa, and the Ootoshi Furutone, all run through the same basin. When it rains hard, they all rise at the same time. If the engineers tried to widen those rivers, there was no room. Tokyo had grown around them for centuries, and the city could not move. If they tried to build higher levees and embankments, the rivers would still overtop them during a major typhoon, because the sheer volume of water arriving in a matter of hours exceeded what any surface system could contain. If they tried to simply route water to the sea faster, the main drainage river, the Edo River, was already near its capacity limits. Standard engineering had already been tried. Levees had been raised. Pumping stations had been built. Canals had been widened. And still, the floods came. The city needed something that had never been built before. So the solution was not bigger pipes or higher walls. It was an entirely new underground river, a parallel drainage system running beneath the real rivers above, intercepting floodwater at the source, storing it in a cavern large enough to hold the Statue of Liberty lying on its side, and then pumping it all, millions of gallons, into the Edo River in minutes when the storm passed. Not a patch, not a repair, a complete reimagining of where water goes. The first phase was understanding what they were dealing with. Before a single shovel broke ground, Japan dispatched teams of geotechnical engineers to study the earth beneath the Saitama Plain. This was not a quick survey. This took years. Research vessels mapped underground water tables. Drilling rigs pulled core samples from dozens of locations to understand the layers of soil, the sand, the clay, the soft alluvial deposits left by ancient rivers. Seismic sensors measured how the ground moved. Ground-penetrating radar mapped buried obstacles, old foundations, forgotten pipes. Every centimeter of the planned tunnel route was analyzed, contested, debated, and reanalyzed. They found that the soil was not uniform. In some places, it was hard enough to tunnel through. In others, it was so soft and saturated that even a small mistake would cause the tunnel ceiling to collapse inward. Every soil sample mattered. Every reading mattered. Every number mattered. Without this data, any tunnel they dug would be a gamble. With it, they had a map of what they were fighting. Then came the design of the tunnels themselves. The engineers planned 5 massive vertical shafts, each one roughly 70 meters deep and 32 meters in diameter. These shafts would act as collection points, each one positioned near one of the overflow-prone rivers above. When a river flooded and broke its banks, water would pour into the nearest shaft, falling down into the underground system below. But designing a shaft that can receive a cascade of floodwater, millions of liters arriving violently under enormous pressure, carrying debris, sediment, and the raw force of a storm, is not a simple engineering problem. The shafts had to be strong enough to absorb that impact without cracking. They had to be shaped to slow the water's descent without creating dangerous turbulence. They had to be sealed at the bottom in a way that directed flow into the connecting tunnel. This was not a drain. This was an engineered waterfall, controlled and deliberate. The construction of each shaft began from the surface and moved downward. Workers used a method called slurry wall construction, injecting a dense fluid mixture into the ground to stabilize the earth while concrete panels were lowered into place. Ring by ring, meter by meter, the walls of each shaft were built downward into the earth. The concrete used was not ordinary. It was a specially formulated high-strength mix reinforced with steel rebar, designed to withstand both the pressure of surrounding soil and the dynamic forces of incoming floodwater. Then came the excavation inside those walls. Crane-mounted excavators dug out the earth at the center, while the slurry walls held the surrounding ground in place. The dirt was hauled to the surface, thousands of tons of it, load by load. Every bucket mattered. Every wall panel mattered. Every weld on every rebar cage mattered. Then came the tunnel boring. This was where the project entered territory that had rarely been attempted in Japan at this scale. To connect the 5 shafts, engineers needed a single continuous tunnel running approximately 6.3 kilometers beneath the Saitama Plain. The tunnel would be 10.6 meters in diameter, wide enough to drive 2 full-size trucks side by side through it. And it had to be bored through unpredictable soft ground at depths of up to 50 meters while disturbing nothing on the surface above. Homes, roads, railway lines, and businesses continuing their daily operations as if nothing was happening beneath them. The machine chosen for this task was a tunnel boring machine, a TBM, not one borrowed from another project, a custom-designed, purpose-built machine constructed specifically for the geology and diameter of this tunnel. It was enormous. The cutting head alone, the rotating disc at the front that grinds through earth, was larger than a 3-story building is tall. Behind it stretched hundreds of meters of trailing equipment, the systems that removed excavated soil, the machines that placed precast concrete tunnel segments, the ventilation and power equipment, the control rooms, the logistics train carrying workers and materials back and forth. The TBM was its own underground city. Operating it required coordinating all of the following simultaneously: the rotation speed of the cutting head, the thrust pressure applied to advance the machine, the volume of soil being extracted, the injection of grout behind the freshly placed tunnel segments to fill any gaps between concrete and earth, the monitoring of ground surface levels above to detect any unexpected settlement, the management of groundwater that constantly seeped through the soil, the temperature inside the machine where workers spent 12-hour shifts, and the constant surveying to ensure the tunnel was advancing in precisely the correct direction. A deviation of even a few centimeters per 100 meters, left uncorrected, would mean the tunnel missed its target shaft entirely. Every millimeter mattered. Every sensor reading mattered. As the TBM advanced, workers behind it assembled the tunnel lining in rings. Each ring was made of 6 precast concrete segments, each segment curved to form a portion of a circle, each one weighing several tons and requiring a hydraulic erector arm to lift and place into position. The segments arrived from factories on the surface, loaded onto supply trains that ran back through the already completed tunnel behind the machine. Ring by ring, meter by meter, the tunnel grew. 6,000 meters of completed tunnel. 6,000 meters of concrete rings, each one installed in ground that wanted to squeeze inward, each one locked against its neighbors under enormous stress. Every ring mattered. Then came the water cistern, the structure that made this entire project legendary. The cistern is the heart of the Metropolitan area outer underground discharge channel. It sits at the southern end of the tunnel system, beneath an agricultural field in Kasukabe City. It is 59 meters long. It is 25 meters tall. It is 78 meters wide. Its ceiling is supported by 59 concrete pillars, each one weighing 500 tons. The cistern holds approximately 670,000 cubic meters of water at full capacity. Those numbers sound like statistics until you stand inside and look at those columns stretching from floor to ceiling in row after row, disappearing into the darkness at the far end. Then you understand what was built here. Constructing the cistern required excavating an enormous underground void in soft, saturated earth, and keeping that void open while filling it with concrete. The outer walls were built first using the same slurry wall technique used for the shafts, forming a rectangular underground box. Then the interior was excavated, one layer at a time, from the top down. Workers removed earth from inside the completed wall structure, installing temporary support struts at each level before digging further. It was like removing the filling from a sandwich without letting the bread collapse. The floor of the cistern was laid last, a massive reinforced concrete slab poured against the base of the walls, thick enough to resist the upward pressure of groundwater that constantly pushes against any underground void. Without that floor slab, the cistern would float. Without those walls, it would collapse. Without those pillars, the ceiling would fall. Every pillar mattered. Every slab section mattered. Every anchor bolt mattered. Then came the pump room, the engine of the entire system. Without the pump room, the cistern would fill during a storm and stay full forever, useless. The pump room contains 4 gas turbine pumps, each one originally salvaged from a jet aircraft engine, each one capable of moving 200 tons of water per second. 4 pumps, 200 tons each, per second. The pumps draw water from the cistern through massive intake pipes, accelerate it through impeller chambers, and force it upward and outward through discharge pipes into the Edo River. When all 4 pumps run simultaneously, they can drain the entire cistern, 670,000 cubic meters of water, in a matter of hours. Installing those pumps required lowering components weighing dozens of tons through access shafts, assembling them in place underground, connecting them to fuel systems, electrical systems, control systems, and discharge piping, then testing each one independently before any were trusted together. The fuel lines were routed underground from the surface. The electrical connections ran through conduit buried in the cistern walls. The control cables linked to a surface operations center where engineers monitor the entire system in real time. Every pump connection mattered. Every control signal mattered. Then came the secondary systems, the parts that nobody talks about but without which nothing works. Anti-corrosion coatings applied to every metal surface that would contact floodwater, because floodwater carries silt, chemicals, and organic matter that eats unprotected metal within years. Ventilation shafts to manage the atmosphere inside the tunnels and cistern during operation and during maintenance, because a confined underground space accumulates gases, loses oxygen, and becomes dangerous to humans without active air management. Drainage systems inside the cistern itself to remove water that remains after pumping, because even the best pumps leave residue. Monitoring sensors embedded in tunnel walls, in shaft floors, in cistern columns, measuring stress, moisture, temperature, and structural movement, continuously, around the clock. Communication systems for the workers who descend to perform maintenance. Lighting systems powerful enough to illuminate a structure the size of an aircraft hangar. Emergency backup power systems so the pumps continue running even if the city's electrical grid is disrupted by the very storm the system is fighting. Every sensor mattered. Every backup system mattered. Every maintenance pathway mattered. Then came the testing. Not a single dramatic moment of turning a switch and hoping for the best, but months of systematic, methodical verification. Each pump was started individually. Each valve was cycled open and closed hundreds of times. Water was deliberately introduced into the tunnel system in controlled volumes to verify flow behavior. Instruments measured how the cistern walls responded to the pressure of stored water. Engineers walked every centimeter of the tunnel, inspecting joints between concrete segments, checking for any sign of water infiltration, marking any surface that required sealing. The control systems were tested under simulated storm scenarios. Operators at the surface running drills, issuing commands, watching system responses, identifying any point where communication lagged or sensors misread. Without this testing, the first real flood would be the experiment. With it, when the storm finally came, the system already knew what to do. The Metropolitan Area Outer Underground Discharge Channel opened in 2006. That same year, it handled its first real flood event. Since then, it has operated during more than 7 major flood events, reducing the flooding area in its service zone by more than 90% compared to the years before it existed. Neighborhoods that flooded regularly throughout the 20th century have not flooded since. The cistern, in its first years of operation, required the pumps to run for extended periods during typhoon landfalls, processing millions of tons of water that would otherwise have been sitting in people's living rooms. Most of the people who live and work above this system have never thought about it. They see a field in Kasukabe. They see a river running calmly through their neighborhood after a storm. They see streets that are dry when they should be flooded. They do not see the 59 columns standing in the dark, bearing the weight of the earth above them. They do not see the tunnel boring machine that crawled through 6 kilometers of hostile ground for years to make this possible. They do not see the workers who spent their careers underground so that strangers above them could stay safe. They do not see the geotechnical engineers who spent years reading soil samples before a single piece of concrete was poured. They do not see the pump maintenance crews who descend into the cistern between storms, checking, cleaning, testing, preparing. They do not see the water they never had to wade through. They do not see the disaster that was quietly, permanently, invisibly canceled. This is what engineering actually is. Not the moment of the ribbon cutting, not the drone footage of a finished structure. It is the years of watching core samples. It is the decade of boring through earth that pushes back. It is the midnight shift of a worker guiding a 500-ton column segment into position 50 meters below a city that is sleeping. It is the knowledge that if any one of 10,000 details was wrong, the whole system fails the moment it is needed most. Beneath Tokyo, the earth holds a secret. The secret is that this city should flood more than it does. The secret is that the disaster you never heard about is the one that was prevented before it arrived. The secret is 6.3 kilometers of tunnel and 59 columns in the dark, standing guard, waiting for the storm. That is what they built. Not just concrete, not just a tunnel, a promise, kept in steel and stone and silence, that the city above will be protected. If you found this story worth your time, subscribe to the channel. Every week we tell stories like this one, about the projects that hold civilization together while nobody is watching. Thank you for watching. And the next time it rains in Tokyo, think about what is happening beneath your feet.